Now that you know what ionic bonds are and what makes up an ionic bond, we're going to look at some properties of ionic bonds as to like what they look like, what kind of melting points they have, what kind of keeps them together, and all that kind of stuff. So let's start off with what are the forces in a solid that has ionic bonds. So when we look at something that has an ionic bond, remember it's a metal and a non-metal. So we are going to have the attraction of positive and negative ions. Remember, ionic bonds, ions. Okay, ions are the metals or non-metals when they lose or gain electrons. This is where we have opposites. Ions attract. And remember then that the same charge ions repel. So an ionic bond is going to take the shape that will limit the repulsions and maximize the attractions between positives and negatives. So when we look at what solids that have ionic bonds look like, okay, we're looking at our picture there on your notes in the right-hand corner. Okay, this is the crystal of sodium chloride. The chloride is the bigger green, and the sodium is the smaller gray. Notice how they kind of take this arrangement that's very repetitive, and it also does not have like charges by one another. It has all opposite charges by one another. So we see this consistent spacing of ions with a very uniform pattern. Notice how the ions are not all the same size. Remember, when something gains electrons, or when something loses electrons, something loses it, it tends to get smaller. Something gains, it tends to get bigger. And then, to start with, atoms are not all the same size. We call these repeating patterns, or these crystals of these ionic solids, crystal lattices. That is the 3D arrangement of ions. Now these ions are locked in place and don't move. They'll only vibrate in place. So that is kind of what an ionic bond looks like. If I'm going to look at a grain of salt really, really close up, you will see these repeating patterns of chlorine and sodium ions, and they'll be stuck together in a very uniform pattern. So now then, let's look at some physical properties of ionic bonds. And the first one is conducting electricity. Well, in order for something to conduct electricity, you have to have freely flowing ions. So if you don't have this movement of ions that can move the charge or move the electricity, it won't conduct electricity, okay? So in the solid state, since the ions are locked in place, they are not going to conduct electricity. But when they're in a solution, meaning they're dissolved in water, okay, the ions are now free to move. Because once something dissolves, it separates. We're going to look at that a little later on in the year. But here, the ions are free to move. And we call these electrolytes. So when you see things like Gatorade, and they say they have all these electrolytes because they have all these ions that are moving. So when we look at a solution, I have all these positives and negatives that are just randomly throughout the solution. Okay, there's no set order anymore. They have dissolved. Water kind of rips them apart. So after water kind of rips apart the pluses and the minuses, you end up with these kind of going anywhere they want to. And that allows the current or the electricity to kind of pass from one to the other. And that is why you don't really want to go outside on a rainy day with a downed power line right next to you. Okay? Water is a very, very good conductor of electricity, especially when it has those salts or those ionic compounds. Ionic compounds are also called salts, okay, which is why NaCl is called table salt. All right, so if we're kind of back to our notes here, I got a little off track there. Let's look at some more properties of ionic bonds. we have melting points, boiling points, and then kind of how hard these ionic crystals are, these crystal lattices. Okay, the first one is when you melt. Okay, when something melts, the bonds have to be stretched. Because in order for something to melt, it has to leave this very lacked crystal lattice structure that you see down here in the lower left on the screen. Okay, so in order to do that, you give all of these atoms a bunch of energy in the form of heat. When they get all that energy, and they start to kind of move a little more. When they move a little more, they stretch apart. Okay, and this stretching apart allows the ions to move. Now the same kind of thing goes if you have a boiling point. In order for something to boil, this is where the bonds between molecules are actually broken because you're boiling something, so they're actually being separated. Okay, I no longer have NaCl together next to an NaCl. I have separate NaCls. Okay, we go from this locked structure again. We totally break all of these little molecules apart, and you end up with them in their gas state. So does an ionic bond have a high melting point and boiling point, or low melting points and boiling points? Well, it's actually very hard to melt like salt, okay, or NaCl. So these have very high melting points. And the higher the melting points are means it took me more energy to break them apart. So a larger melting point means that the particles are more strongly attracted to one another. So a very large melting point on the end of an ionic bond is going to mean that those forces between the two molecules are very strong, so it took me a lot of energy, a lot of heat to get them to melt. Okay. Now we're going to look at hardness. Okay, ionic compounds are very rigid. Alright. Which means they're very set in their ways. Okay, this makes them very brittle. Okay, and they tend to crack when hit. Okay, because I have this nice repeating pattern. So what happens then when you apply a force to it, it realigns these particles. Now the positive, positive, and negative, negative are side by side, so they're going to repel. So now these two repel, and the crystal breaks. Okay, salt crystals are not going to bend. Okay, they crack, they break. All right, which makes them very brittle. All right, now we're going to look at how energy is related to the ionic bond. Okay, and there are types of reactions in terms of energy. Okay, and you should have heard these before. We have one that's called exothermic, and that is where energy is released. These are the reactions that are going to feel warm. And then we have endothermic, and this is where energy is absorbed. And these are the ones that are going to feel cold. Okay. I'm going to look more at these types of reactions later on in the year, but for right now we're kind of just going to look at the exothermic part. Because when you form an ionic compound, that is always an exothermic reaction. Alright, and it works this way because the ions together are more stable than when they are apart. And by more stable, I mean a lower energy. So if you have like Na plus and Cl minus, they're going to be a higher energy than when they are bonded together. So when they bond together, they release this energy, okay, and that is the heat that you will feel, okay. It's always more stable to be bonded to somebody than to be roaming around as a single ion. It takes more energy to be a single ion than when it's bonded to something else. And well, if we try and separate these ionic bonds, like we were looking at in the melting points and the boiling points, and we're talking about whether it takes more energy or less energy, well, that particular type of energy has an actual name, and those are called lattice energies, like the crystal lattice, okay? because this is the amount of energy to separate the ions. So if I have a large lattice energy, that means that I have a greater force of attraction and it's harder to break. The smaller ions, okay, talked about atomic radius last chapter, right? So the smaller ions are closer together and harder to separate. That means they're going to have a larger lattice energy. If we also then look at charge, okay, if you have a larger charge, you're going to have a higher lattice energy. Because usually those are the ones that are smaller, okay, they've lost more electrons, plus they then just have a higher attraction to their other particles, all right? So if we look at this chart that you have there on the right, so if we look at Ki and Kf, Ki is much larger than Kf because I is larger than F. I is in the 5th row of the periodic table, meaning it has electrons out there in a 5p orbital, whereas F only has its last electrons in the 2p orbital. So I is larger, which is why then it takes less energy to break them apart, because these Ki molecules are bigger. They're easier to separate because they don't have as strong of an attraction to one another, okay? Whereas Kf, those molecules are very close together. So they're much harder to break apart because they have a stronger attraction together. If we look at it charge-wise, okay, if you look at NaCl, all right, and Na is a plus and a minus, and Mg is a 2 plus and a 2 minus, okay? Because Mg wants to lose 2 electrons to look like a noble gas, whereas O wants to gain 2 electrons to look like a noble gas. Sodium only needs to lose 1, chlorine only needs to gain 1 to all look like a noble gas. So MgO is much harder to separate than NaCl. I've put in almost 3,800 kilojoules, joules is the unit of energy, to get these to separate in MgO. Whereas for NaCl, I only have to put in 769 kilojoules of energy to separate it apart. So higher charges take more energy to separate. They're usually smaller in size as well. Okay? So let's look at the practice problems. Explain how an ionic compound made up of charged particles can be electrically neutral. Well, that's because your total positive should equal your total negative. And we looked at this before in the earlier video, so this one should be kind of a review. Okay, however many one loses, the other one gains. Well then, describe the energy change associated with ionic bond formation and relate it to its stability. Okay, well what kind of energy reaction do we have here? Are we losing energy or are we gaining energy? Well, we are losing energy. These are exothermic. Okay, they are more stable when bonded. The product, okay, the bonded compound, is a lower energy. Why does NaF have a large lattice energy than NaI? What does this mean? I just mentioned that, okay? NaF is smaller than NaI. So it takes more energy to separate the NaF molecules apart. And the last one. NaCl has a larger melting point than Ki. What does this mean about the property of each bond? Well, if NaCl has a larger melting point, that means that NaCl must have a larger lattice energy because it takes more energy to separate, and in order to melt, I have to separate them apart a little bit so that they can move. So NaCl has a larger lattice energy, which means that it is harder to break or stretch the bonds.